Hello, and welcome to your first Generative Models lecture. Now, before we get into all of the nitty-gritty details, I wanted to give you a brief overview of some really cool things that people are doing with generative models. Generative models are the most common type of model that you're going to hear about in the news, things like ChatGPT or DALL-E that creates images. One thing generative models are really great at is generating new images, for instance, new anime faces or new human faces. And there's tons of different models that do this. More broadly, a lot of generative models create new art, like this one, where I asked it to create a photo of a machine learning professor, and I definitely do not look like any of these pictures. Generative models can also do things like learn how to in-paint images, which basically means they take occluded regions of the image and learn how to produce something that looks realistic to go inside that occluded region. Now, of course, I think the only thing that we've all been thinking about for months and months are large generative text models like ChatGPT. These are increasingly common both in general purpose as well as for specific purposes. For instance, like Copilot, which helps you write code using generative models. In fact, we can stack a bunch of these generative models together, and someone actually did that to create a never-ending episode of Seinfeld, where generative models created the script, the animation, as well as the voices. And we don't have to stop there. Generative models can do things like create music or video game levels. They also do really cool things like style transfer, where you can take the style of one image and apply it to the content of another. For instance, one of my favorite games, Breath of the Wild, has this picture here where you have the style of Starry Night, but the actual image from the game. And when we say generative models, it doesn't necessarily mean we're generating things from scratch all the time. For instance, generative models are also really good at things like aging people's faces up or down. You know how in movies they often do that really annoying thing where they say enhance and they take an image that is already blurry and they zoom in and it's suddenly this like perfectly clear image? Well, actually generative models can sort of do that now. In fact, my husband, who's a video editor, uses these in his work occasionally. Sometimes clients will send over video or images that are just not as high resolution as they need to be. And there's actually tools that can generate higher quality images from a lower quality one. And you may have seen some of these generative models without even knowing it. For instance, Star Wars is really famous at this point for using deepfakes. For instance, in recent shows, they've used deepfakes as a way to de-age actors or to make a new actor look like an old actor. All of these use generative models, and you've probably used them without even knowing because TikTok has a lot of generative filters now. In the past, a lot of the filters that you see on Snapchat or TikTok use something called face mesh, where they basically learn hundreds of different points on your face, and the point of the machine learning in those filters is to figure out where on your face in the video those hundreds of points are. Once they learn that, they can then place things on top, like makeup or a dog's tongue or, pig ears or whatever they want to add. However, there's increasing numbers of filters that use generative models. So it's not that they're placing something on top of your video, rather they're taking your image and they're completely regenerating it with whatever effect it is that you want to have. For instance, the bold glamour filter on TikTok is sort of famous for being one of the first mainstream generative filters on TikTok. And so far we've been talking about some of the positive things that generative models can do, but it's not all good. There are also just tools that can be used by people who have malicious intent. For instance, it's becoming increasingly common to have scam phone calls where they use the voice of a loved one in order to trick someone into sending them money. For instance, if they can get a couple seconds of your voice, then they can call your grandparents and make it sound like you're in trouble and you need them to send you a couple $1,000. And because it sounds really similar to you, it's easy to be tricked. So now that we've seen what generative AI can do, let's talk a little bit about the types of generative models that are out there. Broadly speaking, there are two main types of generative models. The first are density estimation models. In these models, we have an explicit distribution that we would like to learn, and we use the training data in order to learn what that distribution should look like. Once we have this distribution, we can can then sample from it, thus generating new examples. The other common type of generative modeling is sample generation. Here, there's no explicit probability distribution that we're learning. Rather, we have an algorithm that we want to learn how to create realistic images, and we give it feedback on whether we think what it has generated is realistic or not. Now, the good news is it turns out that you already know some generative models. Naive Bayes and Gaussian mixture models, which we learned in 392, are both generative models. Let's look at a quick example from this book, Generative Deep Learning, which talks about using naive Bayes as a generative model. So on the screen, we see a bunch of emojis, and these emojis have some really distinct features, like the color of their hair, the type of shirt they're wearing, and whether or not they're wearing glasses, sunglasses, or none. Remember that the point of naive Bayes is technically to learn a distribution. We learn the probability of each of these different categories. Once we learn that distribution, we can then sample from it to create new emojis. For instance, we could look at the eyewear of the different emojis. We can learn the distribution of eyewear by just counting how many people are wearing glasses, sunglasses, or no glasses. For glasses, there are 22 people wearing glasses, 17 wearing sunglasses, and 11 wearing none. To convert to probabilities, all we have to do is divide by 50. So this is going to be 44%, 34%, and 22%. You can see that we've explicitly learned a probability distribution. In other words, we're doing density estimation. We've learned a discrete distribution that describes how likely it is to have glasses, sunglasses, or none. And we can do this for all of the different features of the emoji, like their hair color. Now, once we've learned all of those, we can use those probabilities to generate new samples. And remember, the whole naive part of naive Bayes is that it assumes conditional independence, meaning it thinks that all of those features like glasses, hair color, shirt style, etc. are all independent. And because of that, it allows us to generate new emojis by sampling from all of those probabilities. And it can even come up with new combinations that we've never seen before. For instance, on the screen, you can see a bunch of new emojis that we generated by using the probabilities calculated on the last page. However, when it comes to generative models, we don't always have that beautifully labeled data like we did in the last example, where we literally had, do they have glasses or not? What color is their shirt? What style is their hair? So let's do another example with naive Bayes where all we have is the raw images. In other words, the pixel values for each of these images. But we can apply a similar idea as we did last time. Each pixel is going to be a feature for us. And what we're going to do is we're going to use naive Bayes to predict what each pixel color should be. Once we learn the distribution of colors for each pixel, we can then sample from it using that assumption of independence. And because naive Bayes has that assumption of independence, it doesn't take advantage of the fact that in images, nearby pixels will likely be very similar to the pixels around it and be a part of the same feature, like clothes or hair. That's something really useful that we might want our generative models to be able to do. Now let's talk about the second generative model you already know, Gaussian mixtures. Remember, the idea behind Gaussian mixtures is that we have multiple normal distributions that are combined together in different proportions in order to create the data that we've observed. For instance, here we have some data on how much money people spend on fast food, and we really have two distributions. First, on the left, we have this distribution of people that tend not to spend a ton of money on fast food each week. And on the right, we have this distribution of people that tend to spend a lot more. When we combine these two distributions, we get the overall pattern of data that we have. The point of Gaussian mixtures is to learn what these distributions are, assuming that they're normal distributions. And once we have those distributions, we can then take samples from them to create new data. For instance, in this example, we might sample this dot from this distribution, and that's a new generated data point. Then we could sample this one, or even sample from the other distribution right here, and another here. Because we're learning an explicit distribution, in this case a normal distribution, we can then take those distributions and create new samples from them. In the two-dimensional case, it might look something like this. Here we have 4 separate clusters of data points, and when we apply Gaussian mixtures, we now have a bunch of distributions, multivariate normals, that we can then sample from. For instance, here, the red points that you see on screen are new generated data points that didn't exist before. Because we learn distributions using the Gaussian mixture models, the new data points are very similar to data points we've seen before, but not all of them are exactly copies of things that we've already seen. Thus, this model can can generate entirely new data that looks like the data we've seen before. So both naive Bayes and Gaussian mixture models do density estimation, and both can be used as generative models. However, they're both pretty simple models, and therefore they're kind of limited. So what if we had a generative model that was a little more complicated, but still did density estimation? Let's talk about one: variational autoencoders. Now, you may have noticed that variational autoencoder is probably using an autoencoder, which is something we've already learned. To review, autoencoders are neural network structures whose goal is basically to learn some compressed, useful representation of our data. In order to do that, they typically will have something like a butterfly shape, where the input and the output are the same size, and the hidden representation is a lot smaller. Thus, we're forcing data through the network. It'll be compressed by the encoder and then decompressed by the decoder. If our model's successful, then it'll be able to roughly approximate the original input once it's been first encoded and then decoded. The job of the encoder is to learn a function, here f of x, that helps take our input x and create a hidden representation that we call h. The decoder's job is to take that hidden representation and learn a function g that basically decompresses the data. And just like before, we mainly care about this hidden representation because the output of an autoencoder, if it's successful, is just going to be the input repeated. What we really care about is this hidden representation that our model has learned of our data. Autoencoders are trained using reconstruction loss. Basically, our loss function is just looking at the difference between our original input and our compressed and then uncompressed or reconstructed output. If our output is similar to our input, then we've learned a really effective way of compressing our data, and therefore the hidden representation will hopefully be useful. Now, you may remember that we don't have to have a hidden representation that is smaller than the input and the output. When the hidden representation is smaller, it's called an undercomplete autoencoder, but we often will use overcomplete autoencoders where the hidden representation dimensions are actually bigger than the input or the output. But we still want the model to learn a useful representation, so we have to apply some type of regularization to our network. One of the ways we talked about doing this is by penalizing the derivative of the hidden representation with respect to the input. Remember, the hidden representation is created by a function that transforms inputs into the hidden representation. If the derivative of this function is small, it means that small changes in the inputs won't result in really large changes in the hidden representation. When that derivative is large, it means that small changes in the input result in huge changes in the hidden representation. And we often want to penalize large derivatives. We want to make sure that similar inputs have similar hidden representations. This means that if two inputs, like two images, are similar, their hidden representation should be similar as well. This helps regularize our autoencoder and help it learn an effective representation despite being overcomplete. All right, enough review. Let's talk about what's new with variational autoencoders. One thing that's really nice about variational autoencoders when they're well trained is that they have things called concept vectors. Concept vectors are vectors that when we move along the vector, we get more and more of that concept. For instance, you can see here a smile vector. As we move along that vector, we get more and more of a smile in our image. Similarly, if we moved in the opposite direction, we get less and less of a smile. This is really similar to the concept we talked about with word embeddings. For instance, in word embeddings, there are typically vectors, like this one here, that represent a certain concept. For instance, here, that vector represents the concept of royalty, because moving along that vector takes you from man, who is not royal at all, to king, who is pretty dang royal. These concept vectors are incredibly useful. So how do we create them? Well, a variational autoencoder has a very similar structure to an autoencoder, but the hidden representation is different. So in a typical autoencoder, we have an encoder whose job is to learn some vector of numbers that is going to be the hidden representation for our input. Then the decoder's job is to be able to take that compressed representation, decode it, and give us something at least very similar to our original input. In a variational autoencoder, instead of learning a static vector of numbers as the hidden representation, we actually learn distributions of values. We call this a probabilistic representation because instead of learning an individual specific value, we're learning a distribution of values. So the encoder, instead of learning a static hidden representation, is learning a probabilistic one. And once we have these distributions, we can sample from them. Then we send those samples through the decoder and ask it to recreate our original image. And we want it to recreate our original image no matter what samples we take from these distributions. For instance, here's an example. We have an encoder that learns the probability distributions for our hidden representation. And then we can take different samples. For instance, here we have this yellow sample that samples all these values here, and then the red sample, which samples all these values here. Now, these samples are really close because they're all sampled from the same probability distributions, but they're not exactly the same. However, when we're training our variational autoencoder, once we take those samples, we send them both through the decoder, and for both examples, we expect that the output they create is going to be very similar to our original input. That means that even though these two vectors are different, they are slightly random samples from the same distributions, we expect them to be able to recreate the same input image. This probabilistic hidden representation helps our model learn that two similar hidden representations should produce very similar output. This is similar to what we encouraged our model to do by penalizing the derivative of the encoder. By penalizing the derivative of the encoder with respect to the inputs, we said small differences in inputs should not cause big differences in hidden representation. With the probabilistic representation of a variational autoencoder, we're saying something similar but slightly different. We're saying that similar hidden representations should generate very similar output. To review, in a regular vanilla autoencoder, our latent representation is static. It's just a single vector of numbers. In a variational autoencoder, we instead have a probabilistic hidden representation where we learn distributions of values instead of exact numbers. This basically means that the encoder of the autoencoder is learning what is the probability of a hidden representation given the certain input, while the decoder learns what was the probable input given the hidden representation that I've seen. And the architecture of a variational autoencoder is very similar to a typical autoencoder. We have an input that is sent through an encoder. The encoder's job is to learn that probabilistic hidden representation. Once we have that hidden representation, because it's a distribution, we can then sample a specific point from it. That point is then sent through the decoder, whose job is to recreate as closely as possible the original image. So let's look at this a little more closely. In a regular autoencoder, we have an input layer and some encoder function, which could be one layer or multiple layers. It then outputs our hidden representation. Again, this is the thing that we're really after. It's basically a compressed or useful way of representing our original information. Then we have a decoder, which again could be one layer or a lot more complicated, whose job it is to take that hidden representation and learn how to recreate that input. In a variational autoencoder, it starts the same way. Again, we have an input. This could be a vector of numbers or more commonly an image. This input is still sent through an encoder, which can be, any type of architecture that we want. However, instead of learning a single vector as the hidden representation, it learns a mean vector, this is the mean of all of those probability distributions, as well as a variance or standard deviation vector. So instead of directly learning a vector of hidden representations, it learns a mean and a variance for distributions. This is because we have that probabilistic hidden representation. That is, instead of learning the exact values of the hidden representation, we learn the parameters of normal distributions, which will allow us to represent that hidden representation with distributions. So our encoder is really learning two vectors of things. Instead of learning a hidden representation directly, it learns the means and the variances of the probabilistic hidden representation. Now, once we have the means and the standard deviations, we have to then sample from that hidden representation. And for reasons we won't go into here, it's actually really complicated to do that. So what we actually do is we take those means and those variances, and we add them together with some noise. This noise is not something that is trained by the model, it's completely random. Thus, our hidden representation, once we've sampled from it, is going to be equal to the mean of the distributions plus the variance times the noise that we've added. This noise term is what allows us to randomly sample from the distributions with mean mu and variance sigma squared. So again, you can think of it as we have a normal distribution and we're learning what the mean is and what the variance is. Once we know what those are, we use this noise vector, which is not something that is trained by the model, to randomly sample from that distribution. Those values are the hidden representation that will then be sent through the decoder. Again, the decoder, like in a regular autoencoder, can be any architecture that is useful for us, but its job is to take this random sample from our probabilistic representation and recreate the input for us. If your brain thinks a little bit better in code than it does math or images, let's go over some pseudocode for what a variational autoencoder actually does. So the first part we're going to look at is the encoder. The job of the encoder is to learn the mean and the log variance of the distribution of the hidden representation. Remember, our hidden representation is just a multivariate normal distribution, and the job of the encoder is to learn what the mean and the variance of that distribution is. Once we know that mean and variance, we can sample from it by generating some random noise and adding it to our means and our variances. What we're doing is using the distribution that the encoder learned and taking a single sample from it. Then we feed the sample to the decoder. The job of the decoder is to take that sample and reconstruct our original output. Because we're taking samples from the hidden representation, it basically tells the model that we expect different samples to create similar images. Even though we're having two random samples from the same hidden representation, we are still expecting the decoder to be able to recreate that original image. So we've gone into a lot of detail about the architecture of a variational autoencoder, but remember, the important thing with neural networks is not just the architecture, but how we're going to train the model. In a typical autoencoder, we use reconstruction loss. This basically just measures the difference between our inputs and our output. In a variational autoencoder, it's no different. We still care about whether our model can accurately recreate our input. However, we also have this second regularizing penalty term. This adds a penalty on the KL divergence of the hidden representation we learn versus the standard normal. Remember, a standard normal is just a normal distribution with a mean of 0 and a standard deviation of 1. To review, KL divergence measures the similarity of two distributions. One way of thinking about it is saying, if we have this distribution, how much information are we going to lose by using this second distribution instead? If two distributions are really similar, we don't lose a lot of information, but if they're very different, we do. So going back to our penalty term, we can basically see that the model wants our hidden representations to be as similar as possible to the standard normal distribution. When these two distributions are similar, this penalty will be very small. However, just like with all of the other penalties we've talked about, it's not that we can't learn parameters that are different from 0 and 1. It's just that if we do have them different than 0 and 1, they better improve the reconstruction loss. Let's look at some variational autoencoders that are trained on the MNIST digit recognition dataset. First, we look at an autoencoder that's trained only considering reconstruction loss. Then we'll look at one that's only trained using that KL divergence penalty. And finally, we'll look at one that uses both. You can see that when we only consider reconstruction loss, we do learn a useful hidden representation. And there's even regions from this latent space that we could sample from that don't really correspond to any digit at all. In other words, we might learn a useful hidden representation, but our latent space is pretty ugly and not well behaved. However, if we only trained on KL divergence, then the representation that we learn is literally just a standard normal distribution. You can see that unlike with the reconstruction loss only model, we don't have pockets that represent similar digits. Thus, this latent representation is also not that well behaved. However, when we combine both reconstruction loss, where we care that the input and the output of our autoencoder are similar, and the KL divergence penalty, we get this really nice behaved latent space. Like with the reconstruction loss latent space, you can see that digits that are similar to each other are close together in the latent space. And like the KL divergence latent space, we have this really nice behavior where things are pretty close together. So why do we want this well-behaved latent space? Well, one thing that can happen when you have a non-well-behaved latent space is that two inputs that are very different can end up having very similar hidden representations. For instance, here we have a square and sort of this rounded triangle, which are very different shapes, and yet their hidden representations are incredibly similar. In a well-behaved latent space, similar inputs will have similar hidden representations, like here, where the rounded triangle and the regular triangle have very similar hidden representations. Secondly, another issue that we can run into is that when we don't have a well-behaved latent space, we can take samples from that latent space that generate outputs that are completely nonsensical and don't look anything like the data we use to train it. For instance, here we have this sample that generates a weird squiggly line that does not look like a shape at all. If we have a well-behaved latent space, then we should pretty much be able to sample anywhere from it, and once it's decoded, it should create an output that looks reasonable. And you can see that probabilistic representation helps with this. Because we're saying that samples from the same distribution should produce very similar outputs, we can have a little bit of this behavior where things that are close together will be similar. The regularization helps create this effect where we have a well-defined latent space that we can sample from at any different point and get a valid output. You can also see that this forces the representations for different types of objects to sort of press up against each other. Thus, if we sample something from the middle, like right here, it should have attributes that are similar to a triangle, a circle, and a square. And you can see here, it really does. So while probabilistic representation helps the model learn that similar hidden representations should generate similar output, regularization helps us have a more well-behaved latent space. For instance, here's some samples from the latent space of a variational autoencoder trained on the MNIST dataset. While these reconstructed numbers are a little blurry, which is a problem with variational autoencoders, you can see that this space has a really nice property. First of all, there's regions of digits that are all similar. For instance, this space is all zeros. You can also see that as we move in a direction of the latent space, we basically morph from one number to the other. For instance, if we look vertically, you can see that we're going from a 0 and then we slowly morph into a 6 and then a 2 and then what looks like a 3 and then an 8 and finally a 9 and maybe something like a 7. This property is incredibly useful if for some reason we wanted to sample something that's a mixture of two categories. Like, let's say we wanted something that was half 3, half 8. We could look in this area of the latent space. So I kept using the words well-behaved as a way to describe the latent space that's generated by a variational autoencoder. But what does that really mean? Well, a well-behaved latent space should really have three properties. First, representation, then realism, and lastly, smoothness. First, an ideal latent space will provide us with good representation. This means that we can take an input, send it through the encoder and then the decoder, and recreate it accurately. This is something that variational autoencoders share with regular autoencoders. But variational autoencoders also have realism. This is the idea that we can sample from anywhere in our latent space, and once we decode it, reconstruct something that looks like a valid input. For instance, in this latent space that was created by training on different shapes, we should be able to sample anywhere from this latent space and get something that looks like a valid shape. Finally, the ideal latent space from a variational autoencoder will have smoothness. Smoothness is the idea that in our latent space, we can pick any 2 points and then gradually move from one to the other, generating realistic looking inputs that slowly morph from the first point to the second. For instance, here we have a drawing of a cat, and here we have the drawing of a pig. In a smooth latent space, we should be able to start from the hidden representation of this cat and slowly move towards the hidden representation for this pig. If we take various samples on that journey, we should basically create outputs that are realistic and slowly morph from the cat picture all the way to the pig picture. So as we move along, we should be getting less cat-like and more pig-like. This process of moving smoothly between one latent representation to another is referred to as interpolation. Now, one cool application of this latent space is in stable diffusion. I wish we had time to cover Stable Diffusion in more depth, but Stable Diffusion is the type of model that you see like DALL-E that is used for image generation. Generally, Stable Diffusion works by taking your input, an image, and learning some representation of it. We then take that representation and add a little bit of noise. We then feed this noisy representation in with a caption, something describing the image. These two are fed into a denoising model. Like the name suggests, the purpose of this denoising model is to predict what the noise was that we added to our image representation. And it's able to use the caption that we provided in order to do that. Once it predicts what that noise is, it can then subtract that noise from our noisy representation to get what it thinks is the original hidden representation of our image. That now noiseless representation is sent through the decoder to create an image. And you might be thinking, well, that's not generating anything, and you'd be correct. The beauty of Stable Diffusion is that once it's done training, we don't actually feed it an image representation plus some noise. We just feed it pure noise along with that caption. This is the prompt that you give to the model to describe what you want. Because the denoising model has learned how to use that prompt in order to subtract noise from our representation to give you an image that matches that prompt, it can still do this even when you feed it pure noise. Thus, we're basically taking a random hidden representation, learning how to subtract noise from it so that it creates an image that matches the caption that we've given it. So why am I bothering to talk about all this? Well, other than the fact that it's interesting, it really highlights one of the useful properties of variational autoencoders. Stable diffusion models often use variational autoencoders in order to learn the image representation. Remember, one of the properties of a well-trained variational autoencoder is that its latent space will have realism. This means that no matter where we sample from that hidden representation, we should get an output that looks realistic. Even when the denoiser is not working perfectly to predict the noise that needs to be subtracted from our image, we still end up with a latent representation that, when passed through the decoder, will produce a realistic looking image. You can imagine that if we didn't have this realism in our latent representation and we learned the incorrect noise to subtract, we could end up with some sample from the latent representation that didn't generate a realistic looking output. By taking advantage of the realism of the latent space of a variational autoencoder, even when our denoiser model is not perfect at predicting what noise to subtract, we still get a realistic looking image once we pass that representation through the decoder. For instance, here's some examples of some random hidden representations sampled from a diffusion model. Even if we added some random variation to these representations, because of the realism of the latent space, once we send these through the decoder, we're still going to get realistic looking digits. All right, one last note before we go. In our convolutional neural networks lecture, we talked about how we often prefer max pooling to strides when we're trying to downsample our images. Remember, max pooling is really concerned with whether something is there, not what is there. So max pooling does not preserve location information. In variational autoencoders, we do often want to preserve that information. So instead of using max pooling to downsample, we'll often use strides. One way to think about it is you want to use strides when you care where things are in an image, and max pooling when you care what is in an image. All right, last example that I want to leave you with. This is a musical variational autoencoder that can take advantage of that smoothness in order to do interpolation. Now, I can't show this for copyright concerns, but I will link it down below so you can check it out yourself. Essentially, what this variational autoencoder allows us to do is take two melodies and then interpolate between them. This means that as we move through the latent space, we're going to generate melodies that are less and less similar to the first melody and more similar to the second until we get all the way to the second melody. All right, that's all I have for you. I will see you next time.